Okay, well, it's my pleasure to introduce our main presentation tonight, our only presentation tonight. Barry, you want to join me? Let's welcome Barry. Barry likes to go by Bear. So I'm really curious, and that'll be your first assignment tonight, to explain to us how you got the nickname of Bear. But before that, in way of an introduction for Barry, I'm going to tell you three things about her, and that's probably all I need to say. You know, she has a master's in information systems. She has a master in the history of science. Oh, I got science down here. Sorry about that. Oh, history of science. Okay. And a bachelor in science in physics. So, excellent. And I'm going to let you explain how those all fold into your presentation tonight. So, Barry, I'm going to turn this over to you. But first, you have to tell us how you got the name or nickname Bear.
Thank you. Yes, my name is Barry, and I do go by Bear. I want to know, is there anybody here who knows another Barry? Anybody here? I can't be the first Barry you know. Anybody else know another Barry? Do they go by Bear? Right. That's how I got the nickname. It's all good. It's all good. So yeah, I'm going to be talking about the James Webb Space Telescope. Let's go ahead and get started. I'm going to do a little bit of history, comparing it to the Hubble Space Telescope. Going to dive into some of the details, including some on the communications. I think that will really pique your interest. I'm sure you can imagine there were a couple of controversies along the way, and then good half of the presentation is going to be going over images and explaining what's amazing about those images. So we all remember the Hubble, I hope. This was about the size of a school bus, and what folded out were the solar panels off on the sides. So that had an 8-foot mirror. It was launched in about 1990. When he said I have a master's in history of science, that was at the University of Wisconsin-Madison. I was teaching in the astronomy department. So I was teaching in the astronomy department 88, 89, 90. And the grad students I was teaching with and the professors were working on the equipment on the Hubble. It was fascinating being there. They were all on the edge of their seats because they knew there could be a problem. There was a little problem. They had to go back up and repair the optics. Oh, by the way, there were other mirrors that were perfectly fine. They just weren't sent up into space. Talk about controversy. So for the Hubble, they were looking mostly at visible light, a little bit on either side of it. But it was a big telescope at the time going into space, so the images were amazing. So for example, here we can see Jupiter from the Voyager flyby, but the Hubble is way more detailed than that. Keep this image in mind because we're going to revisit this. So the James Webb is considered a successor. It's not replacing it. The Hubble is going to stay up, flying its mission for as long as it lasts. It was designed starting after the Hubble optics were repaired, like, that didn't work. Let's try something different. It also had a very different mission, which was looking at things really old, really far away, faint. That's what the expectation was. So it was designed to that purpose. So it's got a 24-foot mirror compared to that 8-foot mirror for Hubble. And now it's looking at infrared. It goes a little bit into red, but it's really, really squarely in their infrared. So why the bigger mirror? Why go to infrared? So now we're going to get into the details. Why does the size matter? Let's go there first. This explanation worked really well last week with the astronomy club. You know why you need a bigger mirror? Because you can see more stuff. It's kind of like, why do you have a big antenna? Because you can hear more stuff. So you're capturing more light, you're getting better spatial resolution. if you think about looking out of a window, you think about being in an airplane, right? You look out your little window on the airplane and you can see this and you can try to roll your eye around and see a little bit farther, but you're really just seeing this. Whereas if you're the pilot sitting up front, you got a nice big window, you got a nice big view. It's the same thing here. Better spatial resolution, all of that good stuff. So those James Webb mirrors are 6 times the area of Hubble's. That's huge for going into space. I mean, that's an engineering feat in and of itself to get something that big into space. So here's a nice little comparison. I love this image. The Hubble, when it went up, was considered gigantic. Sending an 8-foot mirror into space, that was huge. And now here it is, you know, a few decades later, we sent 24 feet up into space. So now we go back and look at Jupiter, that Voyager versus Hubble, and now we look at Hubble versus the James Webb. It's just a completely different image. It's just a totally different view. The auroras scream out at us, right? Like we didn't see them before, now they just shine. Like, wow, there really was magnetism and particles being excited and all that good stuff at the poles. Oh, by the way, that was amazing that it could focus that closely inside our solar system. There was a question whether or not that would work at all, because the intent for this telescope is to see millions and billions of light years away. It's like, can we focus on something that's a few light minutes away? Would that work? It worked. They were super happy with how that came out. You folks heard of redshift? Yeah? Okay, good. So, just for a moment, I understood, was it a couple years ago you guys had the presentation on the satellites? The satellite ham radio. So this is what the Doppler looks like for the satellite. I'm not going to spend a heck of a lot of time here, but as the satellite's approaching, this is in the 440 band. As the satellite's approaching, the frequency is notched up 10 kilohertz. And then as it comes by overhead, it quickly goes from being on the plus side to the negative side, and then it goes on. So that means the wavelength as it's coming towards us is compressed, and then as it goes away, that waveform is spread out. It's a little bit easier to see. I took it out, but it still played for us. Isn't that sweet? For the sound, it's a little bit easier to see or think of in terms of a ambulance coming towards us, right? As it comes in, that waveform is compressed. And then as it goes past, right? So you see the waveform tightened up and then it's spread out. So for light, it's going to do the same sort of thing. So the faster an object's moving away from us, the more the light is shifted towards those longer wavelengths. And so this is a nice graphical representation where we can see the wavelengths spreading out, spreading out. So we throw in Hubble's law, which says the farther an object is away from us, the faster and faster it's moving away from us. Oh, the example in school was always the raisin bread rising, right? Everything starts together, and as the raisin bread cooks, the raisins get further and further apart in ways that are a little bit hard to comprehend, but that's what's going on here, right? So the stuff that's the farthest away from us is moving the fastest away from us. So we put that together with, oh, we can measure the spectrum because Cecilia Payne figured out stars are hydrogen and helium, right? That was over 100 years ago that she figured out hydrogen, helium, that means we can measure this stuff. So we put it all together. We say, in a laboratory, we're going to look for the hydrogen and the helium at these frequencies. Nearby galaxies, it's shifted a little bit. You go farther distant galaxies, that those spectra lines, those absorption lines are shifted more and more to the red. And then in this diagram, what they're calling very distant galaxies are shifted very far to the red, about to come out of the red and go into infrared. With the James Webb, this is quaint, because the shifts are going to be way the heck into infrared, nowhere invisible at all. So here, if we look at this, we go, this is where the Hubble was. You know, this is all we see. RF and microwave are the heck over here. So the Hubble is over here looking at visible, and the James Webb is saying, nah, we're going to look at stuff so far away, we're going to be looking out in here to see how far shifted it is. Let's see, let's talk more about the mirror. Okay, so this is the Where's Waldo picture. Here's Waldo. That's the 24-foot mirror. There's Waldo, right? So these are all of the segments. A couple of the segments are still even around the corner. Did you guys know those are gold mirrors? That's a thin layer of gold on the mirrors. For the Hubble, it was aluminum, because aluminum reflects well in visible light. Gold works great for infrared. They're hexagonal, so they have that high fill factor. So here, there's no spaces. Just think how this would look if they did round mirrors. If they did round mirrors, there'd be holes in all these different places, which would make putting the optics, knitting the optics together and the data together would be difficult. This way, they took care of it by having this high fill factor. Oh yeah, and remember that issue with the Hubble and the optics? They took care of that too. Each one of those segments has some struts, controls. They've got actuators. This sits on the back of the mirror, so the mirror substrate. So now they can control the shape of each segment. That's a good way to take care of the optics problems. And as Elise Fisher at NASA said, if you consider that Webb mirror, that 24 feet, to be the size of the US, each segment is the size of Texas. And the adjustments they have to make are within 1.5 inches. 1.5 inches over the size of Texas. That's some pretty fine adjustment. Let's see if this plays. So these 18 mirror segments act as 18 separate mirrors. Somewhere in here, this will kick in. There we go. So they had to adjust every mirror to make a separate image and focus it. So this isn't quite the process they went through, but this is a fantastic graphic showing the process they went through, saying, let's focus each of them. That is taking its sweet time. There we go. That looks a little bit better. If I keep letting it play, it'll get a little bit clearer. But let's go into this one. So then they had to take those 18 images and focus them all into the center of this primary mirror so that the light would go back into the instruments. I'm not going to get into the details of the issue they had. The first thing they actually had to figure out is which light bit that was coming in was from which mirror, because that first image made it look like it was easy. Oh, we know this piece is this mirror. No, they didn't have a clue. That was pretty hard to figure out. So then they did this process to focus it all into the center and tighten it up. I have a feeling is this the second time through? I wasn't looking. Yeah, okay, let's go on. Okay, so now we have all of that. We've got the telescope, that's all good. Now we have an interesting issue. They're in infrared light. I don't know about you, but I've never heard about an infrared telescope on the soil of the Earth, right? We've got visible light, we've got X-ray, we've got radio, we've got whatever. But we can't have infrared because we're all hot, and infrared is mapping that heat. It can't be on Earth. So this is showing the temperature of, not my hand, but somebody's hand, and saying this part here is about 98 degrees Fahrenheit, and then as we go out the extremities, it's cooler in here, and then it's coolest here. So to capture the infrared light of the stars, you can't have it Earth-based. It's got to be out in space where it's cold. You guys following me on this? Okay, good. So it has to be so cold, it has to be at 53 Kelvin, 53 centigrade degrees above absolute zero. And so how are they going to do that? Right, because the Hubble goes through heat cycles every 90 minutes. It gets blasted by the sun as it rotates around. So that's not going to work. So they did a sun shield. So this, whereas Waldo, is a little bit easier because there's a whole bunch of them and they're down here. So this is the size of a tennis court. Okay, let's think about this a moment. This is going to go into space, and this is the size of a tennis court. I mean, you guys didn't budge on the 24-foot mirror, which sort of blew my mind, but a tennis court, we're going to send a tennis court into space, right? So it's a big sun shield, 5 layers to protect. So is that enough? No, that's not enough. So they had to send it away. So we're 100 million miles from the sun to the Earth, and where they put James Webb at this point. So the Hubble is orbiting at about 400 miles above Earth, and where they put the Hubble is 1 million miles away out in space. There is no going there to repair those optics. There is no going there to repair anything. It's got to work. So this is an image that shows what's going on. So you got the sun here, and we have the Earth going around the sun. That's a year, right? When we go around once, that's a year. And the Hubble is blithely circling around the Earth. Well, for the James Webb, it's in lockstep, more or less, within a certain degree of accuracy. It's going along with us. So as the Earth moves here, the James Webb moves here. Earth moves here, James Webb moves here. So it's not even orbiting us. It's orbiting the sun with us. It's kind of cool out there. But it's still warm. It still gets to 50, 60 degrees Fahrenheit out there on the sunny side. It might get a little bit warmer. So that big tennis court sized sun shield is what stands between the sun on this side, the mirror, all of the instrumentation, right? So it's always pointed away from the sun so that it keeps the instrumentation cool. Those instruments do not work if they get warm. Got great stories about that sometime. And then over here, there's a communications antenna. This is where the solar panels are, the computers, steering, that sort of stuff is over on what's called the hot side. It's never going to get to boiling out there, but it's still going to get warm enough to fry every single scientific instrument that's on there. So, size of a tennis court, and we're sending it into space. Okay, so this is the two side by side. The school bus for the Hubble on the left, the tennis court and that 24-foot mirror on the right. So how do we do it? Oh yeah, the Hubble just had to unfold those mirrors. Folded inside the nose of a rocket. The amazing thing with this is the size of this space inside the fairing is pretty close to the size of the shuttle bay. Within about a foot or so in any dimension, it's pretty close. So they had to fold it. It was the ultimate in origami, but you couldn't grab another piece of paper if it went wrong. So it took 30 days to get out to that place in space. It took 2 weeks to unfold. There were over 300 single points of failure. If any one of those went wrong, we would have some of the most expensive space junk in humanity's history. If any one of those went wrong, that would have been it. Game over, no recovery. So I don't like this. It's too hard to watch that one. Let's do this one. There we go. So that's unfolding the tennis court shade first and getting the, well, they put one solar panel out. So they're going to unfold it, and then after they unfold it, they're going to spread the 5 layers. Here they're obviously going to circle around it. Come on, babies. There we go. We're going to fold out the secondary mirror, fold out the flaps on the primary mirror. Done. For you guys, special information on those communications. So it's 3,000 times farther away from Earth than the Hubble, right? This thing doesn't have brains on it. They didn't send it up with ChatGPT and say, go take pictures. It has to be sent controls. It has to have a way to download that data, right? This is never coming back. So it's going to have about 25 times the download volume that Hubble has. It's got to have a way to store that, and it has to have a way to download it. And how do we download things across space? Radio frequency, maybe? Yeah, there we go, radio frequency. They're going to use the Deep Space Network, so the ground antennas, Australia, Spain, and just north of beautiful Barstow, California. They're using the same shared system that the other deep space craft use, like the Mars rovers. Not Hubble. Hubble's close. It does its own thing. But the deep space stuff. And so since it's that shared system, it's not a question of saying, hey, I want to call home. Hey, I need an update. Hey, I got data to give you. They can't just ad hoc it. This stuff is scheduled 12 to 20 weeks out. They've got to figure out what they want to do, what their times will be for having those frequencies available for either sending controls up or for downloading that data. So they're using the Ka band, they're using quadrature PSK. So instead of just being the 0, 1, 80, it's the 4 corners of the wave. That's at the 2.59 gigahertz. That can send at a pretty decent flip, that 28 megabits. This is for the scientific data. This is for that 57 gigs of data a day. They're going to use this. On the other hand, for transmission and observation schedules, they're using 2.09 gigahertz at 16 kilobits per second. Oh, that's brutal. That's just brutal. And then they're getting engineering data on a different band. That's at a whopping 40 kilobits, right? So that's the system health, that sort of thing. They're all using Reed-Solomon error correction. That's what's used for DVD, Blu-ray, QR codes. What else do we have? Oh, this is a pretty picture from near Barstow. That's 230 feet. In case if you were wondering, you wanted to have one in your backyard. You might have HOA problems with that, or neighbor problems. Aside from space problems, that's 230 feet. And then this is what's on board. So this baby, the Ka band, they call this the high gain antenna. I looked. They weren't fessing up what the gain was, but they did call it high gain. So that's 2 feet across. And then for the S band, it's a little bit smaller. They considered that the mid gain antenna. What else do we have to say here? So the onboard storage is starting at 68 gig on a solid state drive. Their expectation is it's going to degrade over the years, and at some point, about 10 years, expected to be 60 gig. It will just have gotten beaten by the radiation hitting it, the overuse, all of that stuff is going to take its toll. So remember I said that they're scheduling those times and scheduling the observations 12 to 20 weeks out. That's all great, but they can do weekly uploads for commands. Where are we going to point? What do we want to observe? What instruments do we want to use, right? Because there's multiple instruments on the James Webb. And then up to twice daily, they can send command changes. Oh, hey, we noticed that there's a storm coming. Maybe you want to turn a little bit this way or a little bit that way. And they can do those downloads of data. For any of you who are doing satellite astronomy, that telemetry is always broadcast. It's a broad beam telemetry broadcast on that 2.27 gigahertz. So it is striking the whole half of the Earth that's visible to where the James Webb is. Just in case you happen to have, 230-foot telescope in your backyard. No, you don't need that big. You don't need that big. You can have quite a bit smaller than that. Okay, there we go. Exciting stuff for the communications. This was not without its own controversy. So James Webb was a NASA administrator. He happened to be the first NASA administrator. Nonetheless, he was an administrator. Most telescopes are actually named after scientists. So that was sort of a head scratcher. Like, really, you couldn't come up with a scientist to name this after? There were about 1,200 people who signed on and say, so either he was incompetent and didn't realize that his own staff was abusing the LGBTQ community, or he knew and he was complicit. Neither one of them is a good look. So about 1,200 people signed on and said, hey, NASA, will you change it? What's the telescope called? The James Webb. Okay, we know what NASA answered. It was a little bit late, touch late. Started in 96. It was supposed to launch in 2007. 11 years, that'd be fair. Oh, wait, it was 7 years late. And at this point, the price showed up. Oh, we're expecting it's going to be $5 billion. I sort of wonder what it started at for price, but I couldn't find. I could guess it started at under $1 billion. And then it finally launched in 2021 for $10 billion. So it was only a couple years late, 14. That's not bad. It was only over twice the budget. Okay. But it did have those 300 single points of failure. So you got to give them credit that they took care of all of that. So I think we can call it money well spent. Oh, there was a little science problem. They knew that micrometeorites were going to hit. They knew that. They modeled for it and said, we know this stuff is going to hit. We'll be okay. And then within the first couple of months, one hit that was way bigger than anything that was expected. And they went, oh, that was a problem. So they had to realign the mirrors. They had to refocus the mirrors. They had to realign the mirrors. And now they're expecting that they're going to turn away as much as they can when there are meteoroid showers. They hadn't been planning on doing that. They're like, we're good, we'll take it. Sometimes I wonder about that thinking. So my perspective is every time they have to do this sort of thing, every time they have to make an adjustment that's unexpected, that's not for the science, they are taking away from the longevity, whether it's micro or larger meteoroids hitting the mirrors that's degrading the optics, whether it's the fuel being consumed, whatever it is, it's affecting the longevity. And my expectation is that the next space telescope, when I said this, when I first wrote this, I was thinking the next really large space telescope, they're going to design differently. Just like when the Hubble optics didn't work, and they're like, hey, we're going to do something different here. I think because of problems like this, the next time they go to do a really big telescope, they're going to change it. By the way, the next telescope has already been announced, but it's not a big one. It actually goes back to being small. The Nancy Grace Roman, chief astronomer, one of the first chief astronomers at NASA. Okay, we're going to hop into the images. So, everybody want to take a breath? Okay, there we go. I needed to take a breath, maybe. We're going to do this in order from little small stuff, and we're going to keep getting bigger and bigger till we get to the biggest stuff out there. Oh, these are the smallest objects. I think they look like a couple of galaxies. They happen to be my cats. But they couldn't be cuter, sorry. Aww. Okay, let's start with some of the planets. So on the left, this is Mars, by the way. On the left here, this is, well, you can't say this is a photograph. It's more or less a constructed image that's showing part of Mars. And then this is what the James Webb took, where it said, you know, this is where the sun is pointing at this point. So it's glowing from the heat. And then this dark place, the Hellas Basin, is dark because it's 4 miles deep. We don't really have anything like that on Earth, at least not above sea level. So that's 4 miles deep. So if you think like the Grand Canyon, or you think, you know, being in a lake up here in the foothills, when the sun starts going down and we're in the shadows faster than if we were on a hilltop, that's what's going on here. It doesn't get the heat, so it's not glowing quite so much. Let's move on. This is Uranus. Just this by itself is pretty much the best image of Uranus that we've ever seen. So we can see whatever this is, 6 of the 27 moons that can actually be seen around here. Let's go on. This is showing, NASA says, this shows 11 of the 13 rings. I couldn't count 11. They like wandered off into obscurity one side or the other. So why is Uranus so weird? If the sun is here and we're here, we're going around the sun this way, and our axis is off. But it's more or less up and down in the plane that we go around. So we're spinning this way around the sun. Uranus is going this way. So it's a pretty weird, messed up place. This is actually one of the poles. So as it goes around, half of its year is spent with a pole facing towards the sun, and then as it gets around, then the other side is facing towards the sun. So it would be the opposite of what we have here, where our poles are cold and our equator is warm. Their poles are warm and their equator's cold. I wonder if they have jokes there about which way the toilet flushes. So this is Neptune. Again, Voyager, Hubble. Interesting, because to me, the Voyager image is clearer than the Hubble image. And for JWST, it's like, hey, they're rings. How cool is that? And there's a aurora and stuff going on. There's like glowing off of the poles. Like, wow, that's pretty cool. I have a feeling stuff like this was very unexpected. Again, because they weren't sure they'd be able to focus this close. This is an exoplanet. I'll just say it quickly. What's an exoplanet? Somebody say. What? Defiant. Huh. So an exoplanet is a planet that's orbiting any star that's not our sun. Right? So it's like we're looking for other solar systems. So this is another solar system. This is an artist rendering. Honestly, we can't see this well. But this is the first exoplanet that the James Webb found. The James Webb had looked at other exoplanets, but other people had found them. This one was the first one that the James Webb found. And how they found it was by saying, hey, look, we can see starlight, 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 starlight. The starlight goes away. The starlight comes back. Oh, there must have been a planet that crossed in front. It's made a little bit easier to tell when the orbital period is about 2 days. If that orbital period were 10 days, 50 days, 100 days, you'd never catch it. But at 2 days, it's going around and you can see every 2 days that starlight is blocked. And so they can get a sense of the size. By the way, the size of this is almost exactly the same size as Earth, which is like, oh, that's really interesting because that is orbiting really close to that sun. The other thing is the sun, this particular star happens to be a red dwarf, which means it's cooler than our sun. So that means the drop in light is easier to see. If you think about a room that's really well lit, and you shine a flashlight in a room that's really well lit, you're not going to see it. If you turn the lights down and now you take a flashlight and go through, it'll be like, oh yeah, I can see the flashlight better because the room is dimmer. It's the same sort of principle. They did some modeling. I don't want to get into the details, but they did some modeling to say, is this a methane atmosphere on that planet? Because there's something in the atmosphere there. There's all this absorption lines that they're seeing. So they're like, is it methane? Is it carbon dioxide? What is it? And they came back and went, we can't figure out what it is. Okay. That's nice when they try and it, sometimes you can't have an answer. This is the most recent exoplanet. Again, another artist rendering. This one was just found this image was published May 1st. And what's amazing about this particular exoplanet, aside from it's also a red dwarf, it's also a 2-day period, and it's also about the same size as Earth, right? All of those are just mind-blowing that they can find this stuff at, light years away. This has water. Those two graphs, the yellow and the blue, they're trying to figure out if the water is coming from the atmosphere of the planet, or, hold your hats, if that water is somehow coming off of the star. Okay, I had to hit my head a couple times when I heard that. What? That would be pretty mind-blowing, but that's what they're trying to model. Okay, that's it for the little itty-bitty objects. Let's go on to a couple of stars. This star is pretty close by, 10, 20, 30 light years away. And what they did is they put a coronagraph up. So this is actually blocking the starlight. So the star itself is blocked out. Again, think of a bright room and a flashlight, right? If they didn't put a coronagraph up, all you would see here would be white. And it's like, oh, wow, Barry, that's really interesting. Thanks for showing us a white page. So they block out the star itself with a coronagraph and they go, what is it that we're seeing? Isn't that amazing that they can do that? This is 32 light years away. It's a long ways away for being able to see stuff like that. So what they're looking at is a disk around the star that's like this. They're basically looking at the edge of the disk. If we had a different view, it would be like this with the star in the center of it. So they're looking at the edge and going, huh, that's like a lot of gas and dust and stuff around that star that's glowing. They came back and figured out it's some sort of fine dust. But it's an interesting view. I've looked at images in astronomy in a long time. I'd never seen an image like this of a star, a single star. This is a double star. Wolf-Rayets are special. They have elements in them that are heavier than what are expected. It's not just hydrogen and helium. It goes on to nitrogen and other stuff that's pretty unexpected. So this is a binary star system. And unlike many things in space, these are evenly spaced perturbations, like waves. These are evenly spaced waves. There's an 8-year cycle of the binary stars circling around each other, and every time they get to closest contact, they slough off material. So they slough off material, they keep sloughing off material. And so they end up with this even ring pattern, which is only on, half of what we see. The other half, the material's not going that way. This is a different Wolf-Rayet star. This is in mid-infrared. This is a composite. This one is interesting, and they're studying it because they believe that central star is about to go supernova. And so it's sloughing off all of this material. And I think what the astronomers are trying to get at here is that they're going to end up trying to get a range of stars that are different ages that are Wolf-Rayet, and try to piece together a timeline. Just like if we went to the county fair, you'd see people about this height, you'd see people this height, you'd see people this height. And if you just look across the group, you'd be like, oh, that's interesting, humans are all different heights. But over time, if you kept looking, or if you interacted with them, you would figure out some of them are children, some of them are young adults, some of them are adults, some of them are older people, and you'd be able to put together a timeline of what a human's life looks like by looking at and investigating a certain place in time without having to follow those people for 80 years, right? I think that's what they're trying to do here, where it's sloughing off. They know it's going to go supernova, and they'll look for different Wolf-Rayet stars that are in different stages of blowing up, because they want to know after the supernova how much material is left, how much of it just gets obliterated, and what's left afterward and what happens. So I think that's why they took this. Even with that explanation, isn't that gorgeous? Okay, we're going to go on to clusters and galaxies. This is what's called the phantom galaxy. Again, a ground-based image versus a Hubble image. And then we're going to look at a Hubble versus the James Webb. This is what the James Webb is good at. This is what the James Webb was built for. See all of this dust here? It's dust. We can't really see through it in visible light. But in infrared, it clears out a lot of the dust, and we can see sort of the bones or the skeleton. And what ends up is in the center, that's older stars. And they've blown that hole in the galaxy. And then the newer stars, the star nurseries, are out here in the arms. That's the red and the orange. And where the star is formed, it blows these holes, because it's consumed the material that's nearby. And when that nuclear power starts, when the star turns on and starts radiating, it pushes out so much radiation, it clears the space around it. This is the big version of that. This is, somebody thought it'd be fun to put it in hell colors. When I read the article when I found the scientific article that went, seem to go with this image. I think what they were trying to accomplish here is if you take away all of that blue versus red and looking at those different colors, this is gradations of the same color palette. Now those holes really stand out much more strongly than when you've got the multiple colors. And I think they were looking to study the structure of these big holes and try to figure out what's going on that's causing them. But isn't that a great shot? Okay, Stephan's quintet. This is Hubble. This is 5 galaxies. 4 of them are near each other and interacting, and one of them is along for the ride visually, looking out into space. Right, just like if somebody were standing the way the heck over there, how you folks are seated, they wouldn't necessarily be able to tell if our licensed guy in that great t-shirt is actually interacting with these folks here or not, because from that perspective over there, you can't get that spatial resolution to see, is it close, is it not close. That's sort of what's going by here. One of these galaxies is along for the ride, but it's actually nowhere near the other galaxies. So that's how it looked with Hubble. And when we make that dust go away, this is how it looks from the James Webb. Just stunning clarity with that dust blown away. And this is what happens when you get to play with science toys. You get to say, let's take this little piece right here and go, what's in here? What's in this dot? Oh, there's iron, argon, neon, sulfur. Okay, this is groundbreaking. Nobody could do this before. This is totally stunning that they could take a little piece of one image and say, these are the elements in that little piece. You can't do it. It would have been impossible 10 years ago. So they did it. They took this little piece and said, okay, these are the elements here. Totally mind-blowing they did that. But they took it one step further. They're like, what does it look like at that frequency? What's the distribution of that material? Oh, well, this is the distribution of atomic hydrogen. Huh? Really? Yeah, so for this little active black hole, they sliced it and said, this is what the atomic hydrogen distribution looks like. This is what the iron looks like. Molecular hydrogen. I mean, that is unbelievably astonishing that they could take those images and that they shared them with us. Oh, and then somebody must have dropped acid or something, because they said, wow, this was totally cool looking at it in infrared. Let's put it together with X-ray. Really? This was a good idea. So this is taking the Chandra and Spitzer telescope X-ray imaging and putting it together with the infrared imaging, and they learned some new stuff. They learned that there's shock waves going through here, heating the gas to tens of millions of degrees. I know there will always be a smart aleck who says, which scale? Honestly, tens of millions of degrees, the scale no longer matters. It's a lot. And one of the galaxies is winding through the other galaxy at a cool 2 million miles per hour. They would have never found it if they didn't put these images together like this. I mean, that is amazing. And again, if you blow off the science, it's just a beautiful, beautiful picture. Okay, enough for the super high tech. We're going to go back to sort of basic. This is a spiral galaxy. It's got a super clever name. Somebody named it the Great Barred Spiral Galaxy. Really? You're going to have a road called Avenue Road. We're supposedly in a barred galaxy. A barred galaxy just means that the center of the galaxy has an extent this way, instead of just being a circular dot at the center. So this is the physics of high angular galaxies. In other words, remember what I said with that one star where we were looking at it this way? Our image of the Milky Way is this, other than we're in the middle of it. This is saying, let's look at some galaxies this way. So these next few slides are that. So this is the first one. This is the next. And this is the third. So in the end, they're going to do 19 galaxies. They're all at these high angles so that we can see them. And what do I think they're doing? They're trying to figure out how we look. We don't have a mirror that we can put up, you know, like with the animals, like, do you recognize yourself in the mirror? We don't have that. So they're looking at these other galaxies on edge and saying, oh, look, that's interesting. Look at how that structure looks. I think that's what they're trying to do. Okay, dust and other clouds, bigger stuff. I'm guessing you guys have seen some of these images. This is part of the Carina Nebula called the Cosmic Cliffs. And this is how it looked like for the James Webb. Here, wait, let me try that again. You guys didn't say ooh or ah. There's that image. Okay, not where I was expecting the ooh or the ah. But I really appreciate the enthusiasm. You guys are the best. You guys are totally the best. So, what do I want to say here? Nah, let's go. Let's see what else we've got. Oh, no, I do want to say something. Okay, sorry. Let's try that again. Ooh, I'm going to give you guys a hint for when people show you images from space telescopes. Is this a good? Oh, no, I went one too far. Let's go back. See this? I know it's hard, it's a little hard to tell, but there are 8 spikes. 2 up, 2 across, and then 2 at the 45. The James Webb has 8 spikes. If somebody shows you an image and it has 4 spikes on the stars, you can very calmly and coolly say, that's from the Hubble. But how did you know that? Because the James Webb on the stars always has 8 spikes. This is the same sort of thing that we were talking about, where the gas starts to get blown away when the stars form. You start seeing these spaces, and so what's in them is a little bit bluer. And then what's embedded in this particular image tend to be a little bit more purple. Sort of interesting. Interesting color palette choice. Let's go on. The 8-ring nebula. Okay, this is interesting because the star that's actually lighting this whole thing up is over here, not the thing that looks bright in the center. The thing that's bright in the center is causing a lot of perturbations, a lot of wiggle and jiggly stuff going on. This is also called the 8-burst nebula because so far it's burst 8 times. And if you look around and you sort of see the shells, some really smart people have figured out there's 8 sets of shells coming around. So this is how it looked like for Hubble. This image came out in, this was in the first set of images that came out in July of 22. So this is the near infrared, and this is the mid infrared. So just looking at it in different frequencies and saying, oh, that's interesting. We can see some really nice detail in here, and we can see other things here, like the detail that goes into the center of the nebula, right? But the outer part isn't quite so clear. But in July of 2022, this is how they showed them. They're like, look, you can see them side by side. Everybody went, wow, that's stunning. And in December, they're like, let's put that stuff together. Now what do we see? They go, oh, well, this is super interesting because over here what we see, first of all, we can see a lot more detail inside and out. It put it all together with that detail in there and the detail out here. And what they're pointing out is over here, this material is streaming straight out. Okay, well, that's cool. It's streaming straight out. That's nice. Okay, but over here, it's a mess. So there's one nebula, and on one side of it, it's got straight streams, and on the other side, it's all perturbed. Hey, they're going to figure out what's causing this stuff. I don't have an explanation for that. But it was really nice of them to put this image out, whatever that was, 5 months later. It took 5 more months for them to process those two wavelengths together into one image. I love you guys. That is awesome. Pillars of Creation. So that was Hubble. And this is how it, this is a big awe. This one shows really well. This is a stellar nursery where it's red here. Those are where the dust is starting to come together. It's starting to collapse. It's starting to get warmer and warmer. And eventually it will ignite. When it does ignite, it'll open up these holes, like here where there are these holes. It will open these up more and more. So over enough billion years, if the material is dense enough, there won't be any dust left and it will just be a star field. It's just a question of whether or not it is dense enough for it to all form into stars, or if there'll be any dust left at all. Where are we? This is the last nebula. I love this one. Ooh, there isn't an awe to this one. This one is the ooh and the awe all at once. There are not many things in space that look like this. This looks like one of those little time turners. Thank you. I knew you guys would have my back. The protostar is in here, and something is throttling the heck out of it so that the ejections are coming out in these cones on either side. Again, I don't have an explanation for this one. Somebody way smarter than me is sorting this out. But it is really surprising to have something throttled like that at the center and injecting out the material like that. Their comet is those bright filaments that we see are molecular hydrogen that have basically been sent out in shock waves. Like, okay, I believe you. Okay, these are the last few images. Okay, this is a good ooh-ah. Ooh. This was Hubble's deep field image. It took days and days and days of image collection to get this image. And then the James Webb is going to look at one or more of these boxes that are there. So you see the star density here? You see how it looks with the pattern of dots and empty space? Sorry, let me back up. Y'all know what a deep field image is? Oh, that was mixed. I'll go with you don't know. Okay, when I look up in the sky, I tend to look for things. Oh, look, there's a nebula. Oh, there's a star. There's a constellation. Deep field says, we're going to point the telescope to nothing, to a blank space, and we're going to take an image and see what shows up. So we're looking at empty space. This is what's seen. So for the James Webb, they took that one of those boxes. Look at that density of stuff in there. That's how much better the James Webb sees. The size of that image in terms of how big across the sky is it. is a single grain of sand held at arm's length. That's what the size of that image is. And that is loaded with galaxies. This is likely a single dim star somewhere far away. We can tell it's a star because it's got those spikes. The other stuff doesn't have spikes because they're galaxies and they're really far away. So we've got this bit here that's 11 billion light years away. The galaxy is supposed to be 13.8 billion. This little dot here is 12 billion. This little dot over here is 13 billion, and this little dot here is supposed to be 13.1 billion light years away, with the galaxy, or with the universe being 13.8 billion years old. Ooh, Barry, that's amazing. Thanks. I appreciate that. Okay, so what's going on here is they're saying this is where the hydrogen lines are. And what's going on is these are moving further and further off the chart, right? This is presumably pretty near the end of where the James Webb is seeing. And it's going right off the chart. We'll go with that. This was the first deep field. Again, I think this came out in July of 2022 as part of the first set of images. This is the recent images from the last couple of months. They took some region of space. I don't know where it is. They just pointed somewhere and said, this is what we see. And they go, okay, this is what we see. 10 billion light years, 11 billion light years, 12 billion light years, 13.2 billion light years. 13.2 billion light years. This is only a couple 100 million years after the Big Bang. Okay, that's amazing. They did run into an interesting little situation, which is these galaxies are a little bit bigger than the modeling was expecting. By the way, if you've seen the clickbait that says the James Webb disproved the Big Bang, do not click it. It is totally clickbait. But this is going to change how astronomers look at the beginning of the universe and how they do the modeling of the galaxies, because the galaxies are a little bit bigger than they're expecting them to be. Other than that, it did not disprove the Big Bang. Do not click. If it sounded ridiculous, it was ridiculous. There you go. Thank you, sir. You got questions. Okay, you can jump in and be first.
I have lots of questions. First, just an observation. Astronomy has always amazed me because you're looking at the past. You're looking, and I was just, can you put a little perspective in how far in the past you're looking at on the deep field? That's my first question.
Yeah, so let me back up. This is a better image for showing it, just because I think the stuff in here is clearer than the other one. So this point here, I mean, it's 13.1 billion years ago. I'm not sure exactly what you're looking for me to say.
Well, I thought you said it was that far in light years.
Oh, they're just using that as, yeah. So that's a stand-in a distance. So the light left there 13.1 billion years ago and just got to us. Now the deal is during that time, it's moved further away. I haven't gone to look to see how far away this stuff is now, but there's some pretty funky calculations to get at how far away that stuff is now over that 13 billion years that the light took to get to us.
Okay. That's what I was pointing out, is you're never seeing what is actually there now. You're only seeing what was there a long, long time ago.
No, it's a look-back machine. It is definitely a look-back machine. So by now, like if we were sitting at this place right here, what's in the neighborhood of it that we see now might not look like that now at all. Like a whole bunch of this stuff could have easily blown up.
So you'd say that's a long time ago in a galaxy far, far away.
Yes, it's a long time ago in a galaxy far, far away. So I'm going to tell you what you're not asking me. How's that for fun? Do you see these little arcs in here? Those are galaxies that, because of Einsteinian physics, they're gravitational lenses. So basically, because of the mass of what's around them, they're acting as a lens, and everything is being doubled up inside of there. It is wild physics.
Yeah, it is.
Wild.
So one last question, I'll bring us back to the home front. Can you describe briefly what the politics around scheduling time on the James Webb is? Because I'm sure every astronomer out there wants time on that telescope. So how do you get that time?
Well, first of all, you better be at a top research institute somewhere in the world. I'm sure it helps if you're in a U.S. affiliated program that contributed equipment, like University of Arizona has equipment on the James Webb. Or if you're somehow, I didn't talk about it, but if you're somehow involved with the European Space Agency or the Canadian Space Agency, basically if you've had a hand in it, you're going to have a better chance. You also better have a really good proposal of what you want to look at and why it's so special, right? It's not a question of saying, I just want some time. It better be, I want some time because I want to investigate X, Y, and Z, and I can't do it from any other platform. It is going to be super politics. Super politics, for sure. Okay, you're good. Thank you for your questions. Brian.
Yes, we know that Joe K6SAT listens in on telemetry, and I was kind of curious, the amount of time for a signal when it's transmitted here to reach there in these command chains, what is the timing involved, and could Joe listen in on this telemetry?
So the 100 million miles that it takes to go between us and the sun is 8 light minutes. And this is only 1 million miles away, so it's 1% of that 8 minutes. That's the time it takes to transmit. That telemetry is available. Okay, who's SAT? Oh, hi. I watched your presentation. That was really nice. Yeah, if you tune into that frequency that I gave, and if you can see the moon in the sky, it doesn't have to be night, it could be day. As long as the moon is up, then the telemetry will be coming down and hitting all of Earth. You'll be able to get that if you can tune into that, I forget if it was the 2.27 gigahertz. Either that or it was the 2.09 gigahertz. But yeah, if you can tune into that, then you can get the telemetry. Hi, this is where I am in space. You know, whatever it's sending. Yeah.
So just to be clear, I can't pick up the telemetry because my dish is 3 meters in size. Not big enough. But I can pick up the carrier.
Oh, you can pick up the carrier, but you can't pick up this.
And when it was on its way to L2, while it was close, I could pick up the telemetry.
Oh.
Just not anymore.
Is there anybody relaying the signal or no?
No. Just the Deep Space Network.
Yeah. Okay. Go ahead.
Hey, Bear. First of all, freaking awesome.
Thank you.
And for anybody on Zoom, by the way, if you guys have questions, put them here in chat, and we'll get I'll get them relayed here. Just type them out. On one of your graphics, you showed that the telescope is basically showing us its backside, right? And it's faced towards deep space. And it's rotating around, no.
It's not showing us its backside. It's showing the sun its
The sun. Okay, my apologies.
The sun its backside, yeah.
So it's showing the sun its backside and it's rotating around the sun like we are, but it's further out from the sun. So that means, I would assume, that its lunar year is longer than ours, correct?
You mean it's solar year?
Solar year. Sorry, I said lunar year.
No, because it's with us.
Okay, so...
I mean, it might be off by a couple seconds, but...
So my question is, as it travels around, as it makes that rotation, it really only gets, well, if I'm understanding correctly, it only gets one shot a year to look in a certain direction, like up, down, yes, and then left, right. But if it wants to look the other way, it's got to wait until 6 months later.
Oh, yeah.
Is that right?
Oh, yeah.
Interesting. I just wanted to confirm.
Yeah. So that goes into the scheduling. What you want to look at, better have time for where we're pointing. I mean, but you do have however many days that it's looking at a particular area of space, so it can still keep an eye, kind of like for the satellites, right? I mean, it's not a question of it being overhead and you're done and you've got that 1 minute. It's you've got that lead up time, and then the time it's directly overhead, and then you've got however much little more time as it goes past. So there's a duration there, because it is still 365 days to go all the way around. Yeah.
All right, so my question is, because it's out farther, it's going faster, and do you know anything about how they calibrated the GPS or the positioning on it?
I know they calibrated it really, really well. No, sorry. Although it is funny, because when I was really young, I did work in digital signal processing and that sort of stuff, but they're just dealing with it. I did have somebody ask me once if it had brains on board to sort of know how to take care of itself. And I can tell you the answer to that is heck no. It does not have, it has to be told, correct for this, correct for that, correct for this. And then I'm sure you understand the data is coming down and it's being stitched together. Every image that I showed, that's not an image, right? Just like your phone doesn't have photographs on it, your phones, all of our computers are bits, right? That's why we've got those cute filters. Do I make it darker? Do I make it lighter? Can I put bunny ears on? Right? That's all digital manipulation of an image. Nobody's going in a Lightroom to do this stuff. So all that's coming back from the James Webb is a bunch of bits. And they're slicing and dicing it a different way, and they're assigning colors. They're assigning colors to it, and they're trying to be very specific. Should I talk about Alyssa Pagan and Joe DePasquale, or should I not? Okay. The data's coming down, it's being manipulated, right? They're taking raw data and trying to turn it into information, and they serve up these pretty pictures for us to look at, right? Because we can try to wrap our heads around what these images are that we're seeing. Now, whether the researchers actually use that data like that, I don't know. I'm sure to some extent they do look at the images that are created, but to some extent they're going to look at the data and try to make sense of it. So that data comes in and they try to do something with it. There's two people at the STSCI, Space Telescope Science Institute. There's two people whose names showed up repeatedly for the images, Alyssa Pagan and Joe DePasquale. They're the illustrators. They're the designers. They're the, I don't want to call them artists because I'm sure they're scientists as well. They're the ones who are taking that data stream and turning it into these pretty pictures because it's all false color. This is infrared. We don't see infrared. Do you see me glowing? I might glow a little, but I'm not really glowing. You can't see my infrared signature. They're taking the data and turning it into the visual representation. There is one person whose name shows up over and over again besides Joe DePasquale and Alyssa Pagan. There's a woman named Judy Schmidt who's a citizen scientist. This data is available to anybody. You could get this data. Any of us could download this data and do our own image processing. There's a woman who's a graphic designer, amateur astronomer. She happens to live in Modesto, and she actually is responsible for a number of the images that I showed. I didn't point them out, but I gave the credits under the images. And her name has shown up a lot because she did the image processing. So these people are amazing that they're doing this, because otherwise what we would be looking at is pieces of paper that look like this. It would, what are you telling me? 2 more questions. You have to, okay.
If you don't mind, I have one question real fast. What quantity of gold is up there on that thing?
I'm trying to think of a polite answer to that. Probably not enough to make a necklace. I mean, it is going to be microns. It is going to be microns thick. You know, just super, super thin. But that's a great question, and it does have a protective coating over it. Just like the Hubble's, the aluminum has a protective coating. That gold has a protective coating on it as well.
Okay, Barry, you said that the satellite is 100 million miles out following along with us. True?
1 million.
1 million. In my first grade physics class, I remember something about the further away from the sun you got, the slower the planet went. If it went too slow, it'd fall into the sun. If it went too fast, it would take off into space. How do you make that satellite stay with us without falling in? Does the Lagrange point have anything to do with it?
It's in the Lagrange point. It's in Lagrange 2, which is a stable orbital spot between 2 bodies in space.
And
so you take the sun, you take the Earth, there's 5 Lagrange points that are the stable orbital places among the 2-body problem. And then what you do is you put basically little firing engines on there, because I know this is really shocking, but we are not in a 2-body system. There's like a moon and some other planets and stuff. So, you know, they have to fire and do stuff.
Okay, but you do have to have the thrusters to hold it there every now and then.
Oh, yeah, they got it. Yeah, they're doing something.
Let's give Barry a great welcome. Thank you.